In the first video of this final section of MATH0005, I said that what we were going to do was to generalize what we'd done with matrices and vectors. And the concept which generalizes the sets of matrices and vectors that we've worked for is called a vector space. That's what we're going to learn about in this video. So what I'd like to do before we get into vector spaces is to recap some of the notation we used for sets of matrices and vectors, starting with R to the n, which you'll recall meant all height n column vectors with real number entries. So for example, if we were interested in r cubed, r to the power 3, that would contain height 3 column vectors like minus 1, 0, minus pi. That would be an element of r cubed. We'll also generalize that notation a little bit, so f to the n, where f is a field, will mean the set of all height n column vectors where the elements come from the field f. We also had some notation for sets of matrices, and what we did before was to write capital M subscript m times n of R to mean the set of all m by n matrices with real number entries. And of course we'll generalize that to let us talk about sets of matrices whose entries come from any field. So m subscript m times n of f will mean all the m by n matrices whose entries come from the field f, no matter what that field is. Okay, now we're ready to define a vector space. So informally, a vector space is a set which has an addition and a scalar multiplication by some field and a zero vector which obeys the usual rules of vector algebra. But what we have here is a formal definition for vector spaces which captures that basic idea. So here it is. The definition is that if you have a field, which we're going to write as bold F, then an F vector space is a set V which has a special element called the zero vector, and written with a v with a zero subscript v, or sometimes just a zero, an operation called addition, which we usually write with a normal plus sign, and a way to multiply elements of the set v by elements of the field f, which we call scalar multiplication, having the following properties. So for every three elements u, v and w in the vector space V, and for every two elements L and M in the field F, the following 8 rules have to hold. So first of all, the zero element is an additive identity. That's rule number 1 here. That means that if you add the zero vector to any vector V, you get the vector V again. Secondly, the second axiom is about additive inverses. It says that for every V in big V, there exists an X in V, such that when you add X to V, you get the zero vector V. So we often use a notation like minus V for this element X. It turns out that there's one and only one X satisfying the property detailed in axiom 2 here, so we often call that element minus V. The third axiom says that addition is associative. U plus, in brackets, V plus W is always equal to brackets U plus V plus W. The next, number 4, says that addition is commutative. V plus W is always equal to W plus V. And the last 4 axioms concerns the scalar multiplication. Number 5 says that if you do scalar multiplication by the number 1, that doesn't change the vector. Number 6 says that there is a kind of associativity property, namely if you multiply L into the scalar multiple of v by m, then that's the same as multiplying L and m in the field F and then scalar multiplying that into the vector v. Number 7 is a kind of distributivity property for scalar multiplication. So if you add L and m in the field F and then scalar multiply that into v, that's the same as doing vector addition between the scalar multiple L times v and the scalar multiple m times v. And finally, another distributivity property, if you scalar multiply L into a vector sum v plus w, that's the same as the scalar multiple L times v plus the scalar multiple L times w. So these really are just the familiar rules of vector algebra. So what I'd like to emphasize is that r to the n, for any n, with the usual vector addition and vector scalar multiplication that obeys all of these rules. So let's call them axioms rather than rules. One important thing to take from this definition is precisely what you need to give in order to define a vector space. If you want to define a vector space, you have to say which field you're talking about, so which scalars you're going to be allowed to multiply by. You also have to give a set V, which is going to be the vectors in your vector space. You have to give the zero vector, you have to say what that is, and you have to describe the operations of addition and scalar multiplication. So that's quite a lot of information which is needed to define a vector space. Let's look at some simple examples now of vector spaces which we're already familiar with. So first of all, as we've just mentioned, r to the n is a real vector space, so R vector space with the usual addition and scalar multiplication and the usual zero vector. So what I mean by the usual addition and scalar multiplication is that, for example, in r squared, the scalar multiplication, if you multiply a number 2 into a vector 3, 4, then what that is, by definition, is 2 times 3 at the top and 2 times 4 at the bottom. And the usual vector addition just means what you think it is. 1, 2 plus 3, 4 is defined to be the vector that you get by adding the coordinates one at a time. So 1 plus 3 at the top, 2 plus 4 at the bottom. This is what we mean by the usual addition and the usual scalar multiplication. You can check that all 8 of those axioms hold for this set r to the n with the usual addition and scalar multiplication and the zero vector which I've written here, and therefore r to the n is an R vector space. So more generally, f to the n, that is the set of all height n column vectors with entries from the field F, is an F vector space. For any field F, when we give it the usual vector addition, the usual scalar multiplication, and the zero vector just like we had for r to the n. Another example is our sets of matrices, so m by n of F. That is the set of all m by n matrices whose elements come from the field F. And that is an F vector space. Again, when you define a vector space, we have to say what the addition is, what the scalar multiplication is, which field we're allowed to multiply by, so where the scalars in scalar multiplication come from, which field they come from, and what the zero vector looks like. And in this case, it's just the usual vector addition, the usual matrix addition and scalar multiplication, and the usual zero matrix. So let's say when, or with, the usual matrix addition and matrix scalar multiplication, and with zero vector, zero m by n. That means the m by n matrix, all of whose entries are 0. Okay, one final standard example is a slightly silly example, but it's important to remember that this exists. So let's take the set just containing something called 0. So this is a set with one element, just an element called 0. So this is a vector space. Well, I haven't said what the field is. This is an F vector space for any choice of field F. When it's given the only possible addition it can have, which is that 0 plus 0 equals 0, and the only possible scalar multiplication it can have, which is that when you multiply the 0 vector by a scalar, you just get that 0 vector again. So I can completely describe the addition by just saying 0 plus 0 equals 0, and I can completely describe the scalar multiplication by saying that L multiplied into this thing 0 is just 0 again. So that's for any field F, you get this vector space which just has one element, and this is called the zero vector space. Let's now move on and do some more interesting examples, or some examples of vector spaces where the elements don't look like vectors. So it's important to realize that in the definition of a vector space, we never said what the elements of the vector space have to look like. In particular, they don't have to look like vectors or matrices. They can be something completely different. So just because it's called a vector space doesn't mean that the elements have to look somehow a bit like vectors or a bit like matrices. We're going to do some examples on this slide of vector spaces where the elements are not in any natural way vectors. And we're going to begin with an example where the elements are polynomials. So I will write R of x to mean the set of all polynomials in a single variable x with real number coefficients. So that means it's the set a0 plus a1x plus, and so on up to anx to the n for some n greater than or equal to 0, and some real numbers a0 up to an in R. So this is a set of polynomials. These things are not vectors, but when we give this the usual polynomial addition, And what I mean by that is if you had like 1 plus 2x plus x squared, and you added that to 3x cubed minus 2x squared, then the answer would be just what you would normally think it is. 1, what do I have? Plus, I wish I hadn't had a x squared there, let's say 3x squared minus 2x, then the answer that I would get is 1 plus 4x squared. That's what I mean by the usual polynomial addition. So the usual polynomial addition and the usual scalar multiplication this is a real vector space. Again, let me make clear what I mean when I say the usual scalar multiplication. I just mean multiplying a polynomial by a number, like if you had 1 plus 2x minus 3x squared, and you multiplied that by 5, then of course you just get the polynomial 5 plus 10x minus 15x squared. Again, there's nothing special about the real numbers here. So similarly for any field f, the complex numbers, the finite field of order p, the rational numbers, whichever field you like, we can form a vector space f of x, which consists of polynomials of any degree you like in the variable x with coefficients from the field f. So if you're thinking, what is the zero vector in that vector space? Well, of course, it's just the zero polynomial. So the polynomial which is a constant and which the value of that constant is 0. Let's now look at a slight variant on this, this example. So the notation we're going to use is r less than or equal to n of x. So again, we can replace the real numbers with any field you like. So r less than or equal to n of x means the set of all polynomials whose degree is at most n. In other words, all things of the form a0 plus a1x plus, and so on, up to an x to the n, where these numbers a0 up to an are real numbers. That is also a real vector space when you give it the usual polynomial addition and the usual scalar multiplication, as we've just talked about. So the difference between this and our previous example was that in our previous example, r of x here, the polynomials in r of x could have any degree at all. This means for any n greater than or equal to 0. It contains polynomials of any degree you like, whereas r less than or equal to n of x contains only polynomials of degree less than or equal to n. Now we're going to do a completely different example. So we're going to look at another vector space whose elements are not vectors in any conventional sense, and that is the following set. So curly f, like this, is going to be the set of all functions whose domain is R and whose codomain is R. So all functions with a real number input which give you a real number output. I claim that this is a vector space. But in order to define a vector space, you don't just give the set, you have to say what the addition and the scalar multiplication and the zero vector are. So let's define those things. The addition is going to be defined by, if you have two functions f and g, then we're going to define f plus g as the function which sends an input x to the output f of x plus g of x. So this is a definition giving you the meaning of addition in this vector space. It tells you what the meaning of f plus g is. It's the function which gives as output f of x plus g of x when you give it an input x. And we also have to say what the scalar multiplication is. So if I have a real number L and a function f, then I'm going to define L times f to be the function which, when you give it an input x, gives you the output L times f of x. And finally, the 0 vector is going to be the constant function which always takes the value 0. So 0f is the function which, no matter what input you give it, always gives you the output 0. That is a real vector space. If you check every one of those 8 axioms which we wrote up on our second slide, those are all true for each of these examples on this slide. So they're all vector spaces.